Hello everyone. In this video we're going to investigate Kapitza's pendulum, which is an interesting dynamical system that has some pretty unusual and surprising behavior. Essentially it's a pendulum whose support is forced to vibrate up and down at high frequency, and the effect of this vibration is that the pendulum can oscillate not only about the downwards vertical as a normal pendulum does, but also about the upwards vertical. So for that reason you'll also often see this system referred to as the inverted pendulum. So what we're going to do in this video is use Lagrangian mechanics to come up with an equation of motion that describes our system, and use that to try and understand mathematically what's going on and why the vertical position becomes stable. So to start our mathematical description, we need a coordinate system. So I've just put down the usual Cartesian coordinate system as defined on the diagram. Also on the diagram, we've got a bunch of other parameters. You've got the mass of the pendulum bob, m, you've got the length of the pendulum's rod, l, you've got the angle that the pendulum makes to the upwards vertical, theta, and then the displacement of the pivot relative to the origin of our coordinate system is going to be described by this function a of t, and we'll give it a precise mathematical form later on. But for now, just note that the two key properties that it needs to have in order for this vertical position to become stable is that it's a small oscillation. What that means really is that A, or the maximum value of A, is always much less than L, because L sort of sets the length scale of this problem. So we've got a small oscillation, and it also needs to be at high frequency. And again, we'll quantify what exactly high frequency means later on. So if we want to construct the Lagrangian of the system, we need the coordinates of the pendulum's bob and also the time derivatives of those coordinates so that we can get the kinetic energy. So let's do that. Let's write down x and y, the x and y coordinates of the bob. Just using trigonometry, you can see that the x coordinate is just going to be L sine theta. The y coordinate is going to be very similar. There's going to be an L cos theta in there, but you're also going to have to add on this time-dependent A term. So it's going to be A plus L cos theta. Then we want the time derivatives of those as well. I'm just going to use a dot to represent a time derivative. So x dot is going to be L theta dot cos theta. You need that theta dot because you're differentiating with respect to time, not with respect to theta, and so you've got to use the chain rule. For y dot, you have to remember that A is not a constant, right? It's the function that describes the vibration of the pivot. So I'm just going to leave it as A dot, time derivative. Then you're going to get minus L theta dot sine theta. Now, of course, the point of having x dot and y dot is that we can use them to construct an expression for t, the kinetic energy of our pendulum bob. So it's a half times the mass times the speed squared, but the speed squared is just x dot squared plus y dot squared. So then we can just substitute in those expressions that we got for x dot and y dot and move our working up to the top. So we've got t equals a half m. So your x dot squared straightforwardly gives you L squared theta dot squared cos squared theta. Then we need to square this entire y dot term. So you're going to get three different terms. You're going to get your first term squared, which is a dot squared. You're going to get your second term squared, which is L squared theta dot squared sine squared theta, and then you're going to get twice the product of the two parts of y dot, your cross term, which is going to be 2, or minus 2, L a dot theta dot sine theta, and close those brackets. Then you'll notice that one nice thing happens here, which is you've got a cos squared theta times L squared theta dot squared, and you've also got a sine squared theta times L squared theta dot squared, but you can combine those into a single term because cos squared of anything plus sine squared of that same thing is equal to 1. And so you just get half m times, well, let's put our a dot squared first, then you've got that newly sort of combined term plus L squared theta dot squared, and then keep our cross term minus 2L a dot theta dot sine theta. So what about the potential energy V? Well, that's easy because there's only gravitational potential energy in this system. It's just mg times y. We don't even care about the x coordinate. So we just plug in our expression for y that we got before. So you get mg times a plus L cos theta. Now that we've got t and v, all we have to do to construct the Lagrangian is subtract v from t. I've done that here to save you having to watch me write all of that same stuff out again. We've got our Lagrangian here, and so if we want to get equations of motion out of that, we have to apply the Euler-Lagrange equation, and the Euler-Lagrange equation involves partial derivatives of L with respect to both theta and theta dot, so we better find those partial derivatives. So let's start by doing dl by d theta. Which terms depend on theta? Well, you've got explicit theta dependence in this term here. I'm going to expand the brackets at the same time as I do the differentiation. So the 2 is going to cancel with the half in front. You're going to get minus m l a dot, and then you're going to get theta dot, and you differentiate your sine theta, and it just becomes a cos theta. Where else do you have explicit theta dependence? Well, only in this last term here, and cos differentiates to minus sine, but you already have a minus here, and so that term's going to end up positive when we differentiate it. So we're going to get a plus mgl sine theta. Now we also need the partial derivative with respect to theta dot. So where do we have explicit theta dot dependence? Well, you've got it in this second term in your first bracketed group there. And if I differentiate that with respect to theta dot squared just becomes 2 theta dot. So the 2 cancels with the half in the prefactor. And so you just get ml squared theta dot, and you also have explicit theta dot dependence in that final term in the brackets. That one's pretty easy because it's basically just some function multiplied by theta dot, and so when you differentiate it partially with respect to theta dot, essentially all that happens is the theta dot disappears, and so you're going to have minus ml a dot sine theta. So I've just quoted the Euler-Lagrange equation. All we have to do to get our equation of motion is take our partial derivative expressions from the line above and substitute them into there. So let's do that. We're going to have to start by doing some time differentiation of this stuff. And the first term is easy because the theta dot is just going to acquire a second dot because we're differentiating it with respect to time. So you're going to have ml squared theta double dot. We've got to be careful with the second term because a dot and sine theta both depend on time. So we're going to have to use the product rule there. Start by differentiating the a dot, and you're going to get minus l a double dot sine theta. Then for the next term, we'll keep the a dot as it is, so minus ml a dot. Differentiate sine theta with respect to time, and you'll get theta dot cos theta by applying the chain rule. Now the right-hand side of our Euler-Lagrange equation is just dl by d theta. So what I can do is copy and paste our expression for dl by d theta that we got earlier, and there is our equation of motion. We want to do some simplifications before we start analyzing it though. So basically 3 things happen. Firstly, well, the most obvious one is that you've got this minus mla dot theta dot cos theta term on both sides, so those cancel very nicely. You'll also notice that every term has a common factor of ml, so we can divide everything by ml, and it's always nice to put everything on the same side and make your equation have a 0 on one side, so let's do that as well. If we go through all of those steps, you'll get L theta double dot minus A double dot sine theta minus G sine theta is equal to 0. So here's the result of all our hard work so far. This is, by the way, a completely exact general equation of motion. We haven't made any assumptions about small quantities or anything, or even about the form of A as a function of time. A in that equation could be anything. But now, in order to proceed with our analysis, we're going to have to start making it a bit more specific and using the properties of A that I specified earlier, that it's small and it has a high frequency. So the first thing I'm going to do is just introduce some sinusoidal oscillation for A. I'm going to say, let's let lowercase a be some amplitude capital A times cos of omega t, where omega is the angular frequency of those forced vibrations. Now, given that we want the vibrations to be small, we can say that the requirement on capital A is just that A has to be much less than L. And what we really need is the second time derivative of lowercase a, because that's what appears in the equation of motion. So let's differentiate it twice. You differentiate it once, you get a factor of omega out the front from the chain rule, and you also get a minus sign because cos differentiates to minus sine. Then you differentiate minus sine, you get minus cos, but you're going to pull out another factor of omega, and you find that a double dot is just going to be minus omega squared times a cos omega t. This makes a lot of sense because it's saying the second derivative of a is just minus omega squared times this stuff, which is a itself, and that's saying that a obeys the simple harmonic motion equation, which of course it has to, because it just has a sinusoidal dependence on time. You could, by the way, use sine instead of cos for your time dependence of a, or you could even do cos of omega t plus phi and make the phase completely arbitrary, but it turns out that that doesn't affect any of the sort of interesting features of this system, so I'm just going to keep it simple by using cos. So let's combine the two lines up at the top there. what we're going to get is an equation of motion where instead of a double dot, you have an explicitly time-dependent term. Your equation is going to be L theta double dot, and then plus omega squared capital A cos of omega t times sine theta minus g sine theta is equal to 0. So here's where we're going to start making some approximations, and I've just written down that we're going to try a solution of the form theta, as it depends on time, is the sum of two different functions, theta naught of time and delta of time, and theta naught and delta each have special properties, and I'll tell you what those properties are and then explain why they're reasonable. And essentially, so theta naught is going to be a term that varies slowly in time, so I'm just going to write slow, and it's not going to be small, right? It's going to be large. If it's an oscillation, it's going to be a large amplitude oscillation, but it doesn't even have to be an oscillation, right? It's just some general term that varies slowly and can have a large magnitude. Delta is basically the opposite. It's a term which varies very quickly, varies on a short time scale, and it has a small amplitude, and we're going to say that it is an oscillation, right? So we've got our solution being split into two parts, a slowly varying term with a large amplitude and an extra little bit added on, which is a quickly varying small amplitude oscillation. Now, if you think about it, you should be able to convince yourself that if you take a function that has those properties that we were just describing, in other words, can be split into those two different parts, the slow large part and the fast and small part, if you were to plot it as a function of time, it would look something like this little sketch that I've drawn out here. So you've basically got this overall waveform that looks a little bit like a sine wave, but it could really be anything. But then superposed on top of that overall waveform, you've got these tiny little oscillations, but those oscillations don't really affect the overall shape when viewed on a long timescale. Now, as for why that's a physically reasonable functional form to guess for theta of time, I think there are really two reasons. One is that your perturbing function a of t is small, and therefore you might expect that the solution you get looks a little bit like the solution that you would get without any vibrations, but with some extra little perturbations to your solution, which would take the form of high frequency oscillations because the perturbing function is a high frequency oscillation. So you would kind of expect to get something like this just on intuitive grounds, but also we can motivate this solution based on experimental observations. And what I mean by that is that I think at the time when Kapitza came along and actually explained all of this stuff mathematically, the behavior of the inverted pendulum when it's driven at high frequency had already been known for quite a long time. So people knew how this pendulum behaves, right? They could already make graphs of theta as a function of time, essentially, but it's just that no one had actually come along and explained it until Kapitza did his mathematical analysis. So presumably when he was coming up with his original solution, he was also sort of inspired by experimental results when he was coming up with sensible forms to guess for this equation of motion. But this idea of separation of timescales is going to be key to actually solving our equation of motion, and we'll make that a bit more concrete in a little while. So let's get back to our equation of motion and notice that sine theta appears in two different places in that equation of motion. Therefore, it's going to be important to figure out what we're going to do about sine theta. Now, let me just write this down. So then, sine theta, well, given the functional form that we're guessing, sine theta is, of course, just sine of theta naught plus delta, but we're also saying that delta is a small quantity compared with theta naught, and so what we can do is a Taylor expansion of sine of theta naught plus delta. So the first term in that expansion is just, of course, sine theta naught. Then we're going to have to add on delta multiplied by the derivative of sine theta naught with respect to theta naught, but that's easy, it's just cos theta naught, so plus delta cos theta naught. I guess I should, of course, make this a wavy equal sign rather than exact equality, because there would be a delta squared term, and so on and so on. But delta is small, so we can just do a first order expansion here. So we can now come up with our sort of overall equation of motion in terms of theta naught and delta, and our starting point is going to be this equation of motion that we had before. I also want to divide everything by L so that our second time derivative terms just have a coefficient of 1, and so you're going to start off with theta naught double dot plus delta double dot, just replacing theta with theta naught plus delta. Now we want to write this out explicitly term by term, so we're going to have a plus omega squared a. Remember, we're dividing everything by L, so omega squared a over L. We've got our cos omega t there, And the sine theta, I'm going to first write in our sine theta naught, right, from our Taylor expansion. Then I'm going to have an entirely separate term with the delta cos theta naught. So I'm going to do plus omega squared a over L. Then we've still got our cos of omega t, but this time we've got delta cos of theta naught. Then we've got minus g sine theta. So again, we get two terms from that by just substituting this Taylor expansion in place of sine theta. So we're going to have minus g over L sine theta naught, and then minus g over L cos, I forgot my delta, and then cos of theta naught. And all of that is now approximately equal to 0. I've had to clear a bit of space, but I've kept the key information here, which is the functional form that we're guessing and the resulting equation of motion that we get. So one fact that we haven't really made use of yet is the fact that A of t is oscillating at a high frequency. That is going to allow us to ignore some of the terms in this equation of motion and make a bit of progress. So I've just written down here that some terms are negligible at high frequency. We're also now at a point where we can quantify what we really mean by high frequency, because if you think about it, you've got a couple of terms proportional to omega squared a over L. The other terms, well, the terms on the right-hand side of those are proportional to g over L. And so we could ignore the g terms, provided that omega squared times a is much bigger than g. That will allow us to just ignore those g terms. As it turns out, though, those are not the only terms that you can ignore. So let's go back to our big equation of motion and look at it term by term and figure out which terms we are going to ignore and which terms would not be valid to ignore. As a starting point, let's think about theta naught double dot compared with delta double dot. Can we ignore either of those? Well, remember that theta naught is supposed to be varying slowly, while delta is supposed to be varying very quickly. So imagine that theta naught and delta are each oscillating with their own characteristic angular frequency. Now we know from the simple harmonic motion equation that if you differentiate an oscillating term twice, you get a prefactor of the angular frequency squared of that term. Now delta has an angular frequency which is much greater than the angular frequency of theta naught. That's just part of the definition of theta naught and delta, right? Delta is just varying on a much faster timescale. When we square those angular frequencies, that discrepancy becomes even bigger. And so it's safe to say that theta naught double dot, even if theta naught is not negligible compared with delta, theta naught double dot is negligible compared with delta double dot, right? So I'm going to ignore that first term and just start my simplified equation of motion with a delta double dot. Now, what about the next two terms in my original equation of motion, this one here and this one here? How do they compare with each other? Well, they're mostly the same. They've got the same prefactor. One's proportional to sine theta naught, one's proportional to cos theta naught, but we can't assume that theta naught is small, right? And so we can't really say anything about sine theta naught versus cos theta naught. However, the second of those two terms is proportional to delta, while the first term doesn't have a factor of delta, but delta was assumed to be small. So we may as well ignore the second of those two terms that I just underlined, and we'll just get delta double dot plus omega squared a over L cos of omega t sine theta naught. And we already said we were going to ignore the g terms, and so that is just approximately 0. A very nice simplified equation of motion that is going to allow us to figure out a sensible functional form for delta. And that's because, well, you can just keep the delta double dot on its own on one side, move the other term to the other side. All that's going to happen, of course, is that it picks up a minus sign. So delta double dot is approximately minus omega squared a over L times cos of omega t times sine of theta naught. Now, of course, this equation in general is hard to solve. In fact, it's kind of impossible to solve exactly because we don't know how theta naught is varying in time yet. However, let's use this idea of separation of timescales again. We know that delta is varying much more quickly than theta naught. So from the point of view of a single oscillation, or even a couple of oscillations of delta, theta naught is not going to be changing that much. And so we could just assume, for the purposes of sort of integrating this differential equation for delta, we could just assume that theta naught is constant, because over the time scale on which delta varies, theta naught doesn't really vary that much. And so if we just integrate this twice, you're essentially just integrating cos omega t twice. When you do that, essentially it's just going to make the minus sign disappear, and it's going to make the omega squared disappear, because if you integrate cos omega t, you get sine omega t divided by omega. That makes one of the omegas disappear. Then you integrate sine omega t, and you get minus cos omega t divided by omega. And the conclusion is delta is roughly A over L cos of omega t sine of theta naught. Again, that separation of timescales was a key idea in solving that. We assumed that theta naught is a constant for the purpose of doing that integration. It's also reassuring to note that our solution for delta has come out sort of consistent with the assumptions that we made, in the sense that we said earlier that A over L was much less than 1, or really we said A was much less than L, but that's the same thing. And we also said that delta is supposed to be a small quantity, and delta has indeed come out proportional to something that we said has to be small. So our assumptions are looking pretty self-consistent here. Okay, so just to summarize what we've got on the screen at the moment, at the very top, we have our functional form of our trial solution for theta, which is, remember, what we're aiming to solve for, right? Theta is a function of time. On the next line over here, we've got our overall equation of motion that governs how theta naught and delta vary with time. And what I've just added here is what we just solved for, which is the approximate time variation of delta. So now we're going to take that idea of separation of timescales even further and use it to make some of the terms in our equation of motion disappear, and to make others take on a more simple form. And the way we're going to do that is time average our equation of motion over some short time period of the order of 1 period of oscillation of delta. In other words, we're averaging over a time which is about 2 pi over omega, or maybe some integer, small integer multiple of 2 pi over omega. Now, why is that a sensible thing to do? Well, essentially it's because theta naught is just varying on a much longer timescale than delta is. And so if you care about the long-term time evolution of theta naught, you wouldn't really intuitively expect that to depend on the very fine details of what delta is doing over a very short time period. You would expect the oscillations delta to have some effect on what theta naught is doing, but the fine details shouldn't really matter. And so it seems like a sensible thing to do to just consider the time averaged effect of those oscillations. So let's take our equation of motion and time average each term over this short time period. The delta naught double dot term, what's going to happen to that? Well, nothing's going to happen to it because it's varying on long time scales. And so if we average it over a very short time, nothing really changes. And so we just keep our theta naught double dot as it is. The delta double dot term, however, is going to just become 0 because delta is varying sinusoidally. It's proportional to cos of omega t. If we differentiate it twice, it's still going to be proportional to cos of omega t. And when you average a sinusoidal function over time, it just goes to 0 because it spends equal amounts of time above and below your time axis. And so delta double dot is going to go to 0. Similarly, this next term is going to go to 0 because it's got a cos omega t, and that's going to average out to 0 as well. Now things get a little bit interesting with the fourth term in our equation of motion, and that's because, well, we know that delta is varying in such a way that's proportional to cos of omega t, but there's already a cos omega t in that term in the equation of motion. So overall that term is proportional to cos squared of omega t. So it doesn't average out to 0 because cos squared is always positive. So let's figure out what exactly it is. I'm going to start by keeping my prefactor plus omega squared a over L. I'm going to keep the cos theta naught term. Again, nothing happens to that when we average it over a very small time period. Then what contributions are we going to get from the delta? Well, let's just put multiplied by. You've got your a over L from the delta. You've got your sine theta naught from the delta. And then all that's left is this cos, and we're going to combine those into cos squared. I'll just put angle brackets to show that we're averaging cos squared omega t over time, like that. Now, remaining terms, the g terms in our equation, the minus g over L sine theta naught term, again, nothing's going to happen to that, but the final term is proportional to delta. Delta is oscillating sinusoidally, and so that final term goes to 0, and all of this is approximately 0. Now, how does this tidy up? Well, let's write out all the terms in their simplest form. Theta naught double dot is, of course, the same. Time average of cos squared is just a half. You can kind of argue that based on symmetry, or you can just do the time average of cos squared using integration, but I'm just going to quote that result here, that the time average is just a half. So gathering all of those terms together, you get plus omega squared a squared over 2l squared times sine theta naught cos theta naught. Then we've just got our minus g over L sine theta naught, and that's approximately 0. There is our time averaged equation of motion. But this is nice because we have an equation of motion that only involves theta naught. It doesn't involve delta at all because we've separated it out based on timescales. So if we only care about the long-term behavior of the pendulum rather than the very fine details, we can just now forget about delta and just solve this equation, or at least investigate the behavior of this equation of motion in terms of what theta naught is doing. So it's a differential equation, so of course we ultimately want to integrate it, but it's hard to integrate in its current form because the second and third terms depend not explicitly on time, but they depend on theta naught, while the first term is a time derivative. So we can't really integrate with respect to time or with respect to theta naught because it will only work for some of the terms. So what we can do in cases like this is a useful identity, calculus identity. It's probably worth remembering if you do a lot of these mechanics problems. It's that the second time derivative of theta naught is the derivative with respect to theta naught of a half theta naught dot squared. Now you can convince yourself that that works by just evaluating the right hand side and using the chain rule. I won't go through all the details of the proof here because I've talked about it on various occasions in the past, but I think it's a sufficiently commonly used identity that I'm safe to quote it here, and you can probably prove it pretty easily yourself. So why is that useful? Well, it's because then we can integrate the top line, the equation of motion on the top line there, with respect to theta naught. The first term, the theta naught double dot, just becomes the stuff in the brackets in my identity here, right? Because when you integrate the right hand side of that identity, it just makes the d by d theta naught disappear. So that's pretty nice. You get half theta naught dot squared. Now, as for the second term, well, let me start by writing the prefactor, omega squared a squared over 2l squared. Now, this is actually nice to integrate because cos is the derivative of sine, and so sine theta naught cos theta naught is like something that you would get by differentiating a function using the chain rule. So we can kind of think about the chain rule in reverse. In particular, think about what you would get if you were to differentiate sine squared of theta naught. You would get 2 sine theta naught, then you'd get your cos theta naught from the chain rule. So all I have to do to make this integral work out is divide that by 2 to cancel the 2 that you would get from the power rule when you bring it down from the power. And finally, well, minus g over L sine theta naught. Sine integrates to minus cos, and so that makes the sign positive at the end. So plus g over L cos theta naught. And this is now, well, it's no longer 0. It's approximately some constant. We don't know what the constant is without further information, though. Now, what are we going to do with this? Well, we can get a bit of a hint from this first term, half theta naught dot squared. That might remind you a little bit of kinetic energy, which is half mv squared. So what we could do is multiply our entire equation by something that makes the first term look like kinetic energy, so that we could then interpret the other terms here as a potential energy, and then this equation would just be expressing the conservation of energy. So what I'm going to have to do is multiply by, well, definitely a factor of m, but also a factor of L squared, because the linear velocity of the bob is L theta naught dot. Again, we're ignoring the delta, the little oscillations. We're just pretending now that, well, we only care about the long-term behavior of theta, and so we're focusing on theta naught, right? So the kinetic energy is approximately a half ml squared theta naught dot squared. We have to, of course, multiply all of the terms by ml squared then. So we're going to end up with m omega squared a squared. You've got a 4 over on the denominator, but the l squared disappeared. And then you've got your sine squared theta naught, and your final term is going to be plus mgl cos theta naught. It's still approximately constant. It's a different constant, but it's still a constant. And then the idea is that our pendulum is essentially moving in some effective potential, which I'm going to call u of theta naught, right? The effective potential energy, which is approximately just the stuff that's not kinetic energy, right? Because you can interpret this equation as just saying kinetic energy plus something is a constant, so the something must be a potential energy, right? So it is approximately m omega squared a squared over 4 sine squared theta naught plus mgl cos theta. Again, this makes quite a lot of sense because this mgl cos theta is just gravitational potential energy, which is the potential energy that you would get in the absence of the small vibrations. And this first term is sort of the time averaged extra potential energy that you get when you introduce the vertical vibrations. So why do we care about this potential energy function? Well, if we care about stable and unstable equilibrium positions, then the shape of the potential energy function can, well, tell you all about that stability. So let's find the positions of equilibrium, which are the stationary points of the potential energy function, and then we'll figure out whether they're maxima or minima, and therefore figure out whether or not they are stable. So the first thing we need to do is differentiate our potential with respect to theta naught. Again, I should use approximately equals. In fact, I'm just going to use normal equals from now on. We'll just implicitly understand that it's really approximate, because this whole thing is approximate. Your first term, you're going to get m omega squared a squared over 2 times sine theta naught cos theta naught, using the chain rule. Then you're going to get minus mgl sine of theta naught. So we want to set that equal to 0 if we want to figure out where the equilibrium points are. It would, of course, also be useful to factorize it, because there's a common factor of sine theta naught. I'm going to choose to factor out half m sine theta naught. That makes things work out pretty neatly, because then your first term just becomes omega squared a squared cos theta naught. Your second term then becomes minus 2gl. You have to pick up a factor of 2, because I chose to factor out the half just to make it look a bit nicer. So we're trying to set that equal to 0 to find the equilibrium positions. Then there are various different cases for which this equation is satisfied. So the first case is when sine theta naught is naught. Of course, that happens when theta naught is just naught itself, or it's pi. Then, of course, any multiple of pi will do, but physically 0 and pi are the only two distinct ones, basically meaning there are equilibria at the very bottom and the very top, right, when the pendulum is vertically above the pivot and vertically below the pivot. The other case, of course, is when the bracketed term is 0, and that gives you the condition that there's an equilibrium when cos theta naught is equal to 2gl over omega squared a squared, just some positive quantity that depends on the various parameters of the system. It is worth, I think, pointing out at this stage that the 0 and pi solutions would have existed without the vibration. So just for like the classic simple pendulum, this extra solution has been introduced by the vibration, so that's kind of interesting, but it's not the most interesting feature. The most interesting feature is the stability of the theta equals 0 position, which is what we're going to investigate next. Right, so for stability, we care about the second derivative of the potential energy, so d2u by d theta naught squared. I'm going to do it using the product rule. We've got this bit and this bit, and I'm going to take that as my sort of u and v in my product rule formula. So first we differentiate the bit outside the brackets, and we get half m cos theta naught. Then let me just copy and paste the bracketed stuff, because we're going to leave that unchanged. Then we're going to have another bit where we keep the half m sine theta naught, but we differentiate the stuff inside the brackets. Now, when you differentiate the stuff inside the brackets, the constant term will disappear, and you'll just get omega squared a squared times minus sine of theta naught. And if you times that by half m sine theta naught, you're going to get minus half m omega squared a squared, and then sine squared of theta naught. So there's your second derivative of the potential. So now all we have to do is take the 3 different theta naught values that we derived for the equilibrium positions and substitute them into the second derivative to see whether it's positive or negative, and therefore understand the stability of those points. I want to start off with the cos theta naught equals 2gl over omega squared a squared point, because that's actually pretty easy to deal with. If we take that and substitute it into our second derivative, so d2u by d theta naught squared, then what's going to happen is omega squared a squared cos theta naught minus 2gl is just going to be exactly 0. So we don't even need to actually do cos inverse. We can just see that the bracketed term will be 0, and so your second derivative is only going to consist of the part outside the brackets, right? So this minus half m omega squared a squared sine squared theta naught, where theta naught is the angle that satisfies this particular condition. But regardless of what that angle is, this is all squared stuff, and m is a positive quantity, and that means that overall your second derivative is negative. If the second derivative is negative, that means you've got a maximum point in your graph of u against theta naught, and if you've got a maximum point, that corresponds to an unstable equilibrium, right? So you do have this extra equilibrium position introduced by the vibrations, but it's always unstable, right? So next one, let's consider what happens when theta naught is pi. Then your second derivative, let me save some time by writing it as u double dash, second derivative of u. Well, you've got cos theta naught, cos of pi is -1, so you start with minus a half m. Then again, cos theta naught is -1, so you've got minus omega squared a squared minus 2gl. Then the sine squared bit, well, sine of pi is 0, so that bit just disappears. You've got a negative thing outside the brackets, you've got a negative thing inside the brackets, and you multiply two negatives together, you're going to get a positive number. So that's bigger than 0, therefore you've got a minimum point, and that is always stable. Again, it makes intuitive sense. It's the same as what you'd get in the classic simple pendulum. It's just saying that the bob can hang vertically downwards in a stable equilibrium. So I've saved the most interesting part for last. Now we have to consider what happens when theta naught is 0. It's the result that we've been waiting for. Well, our u double dash is, well, cos of 0 is just 1, and so I've got half m, positive a half m outside the brackets. Again, cos of 0 is 1, so we've got plus omega squared a squared minus 2gl in the brackets. Again, sine of 0 is 0, so that bit disappears. And you've got two terms in the brackets that have opposite signs. And so the stability of this point can vary depending on how high the frequency is. Now, the condition for stability is that we've got a minimum in the potential, and therefore this quantity is positive. So it's stable if and only if omega squared a squared is bigger than 2gl, or if we want to rearrange for omega, that's like saying omega has to be bigger than this critical value, the square root of 2gl over the amplitude of the oscillations a. So you always have this equilibrium position at the very top, but it only becomes stable once you drive the pivot of the pendulum up and down at a frequency greater than this critical frequency that we've just derived. I'm just going to finish off by giving a little rearrangement of this condition for omega. So you could write it as omega squared a over g times a over l is bigger than 2. Why am I saying this is interesting? Well, it's because this quantity omega squared over g, we specified earlier that is what has to be large in order for our analysis to be valid. If you look back earlier in the video, we said omega squared a is much bigger than g. But we also said, in fact, right from the beginning, that a over l is a small quantity, a very small quantity. So you've got the product of something which is much bigger than 1 with something which is much less than 1 has to be greater than 2. And I just find this form of the condition kind of interesting because it gives us a sort of more concrete bound on these limiting quantities, omega squared a over g and a over l. Okay, so I think that's enough for this time. It's been a pretty involved analysis, so well done if you've made it this far. I hope this has helped you to understand this fairly complicated and interesting system. Thanks for joining me, and I'll see you again soon.